Section 10.4, polar coordinates and polar graphs. Do you know anything about polar coordinates? Battleship?
Yeah, like when you play Battleship?
No, when you do Battleship, you're using rectangular coordinates. Because when you do Battleship, you're doing like I-12, right? So to do I-12, I don't remember which way it goes. You go across and then down. That's rectangular.
That's what I do.
Right.
What about a sonar like on an actual battleship?
Sonar on an actual battleship probably uses polar coordinates.
Close.
So what do? How does that work?
Sends out a signal and it bounces back.
And then how do they determine where the ship is?
It's on tree to bounce back based on the wavelength.
True, but then how would they? If your ship is going this way and that ship is over there, how would they?
The angle at which it returns.
They would tell the angle, and they would tell the distance, and that's polar coordinates. We're used to dealing in rectangular coordinates. In rectangular coordinates, we do things like this. We go, that might be the point 5, 1. We go over 5 and up 1. Or we might call this point right here 0, 3. We go left and right 0, straight up 3. Those are called rectangular coordinates. Today, we're going to talk about a different graphing system. The graphing system called polar coordinates. The way polar coordinates work is we describe points by using two things. We're going to use r and theta. So instead of using x and y, we're going to use r and theta. What do you think r stands for? The radius, which is the distance from the origin. And obviously theta stands for the angle. So for example, this point right here. What would you call that point right there? I think I count 8 little circles out. So that would be the point 8, comma, pi over 6. How about this point? In rectangular coordinates, that would be the point 0, 3. I started at the origin and I went 3 straight up. What would we call that point in polar coordinates?
3, pi over 2.
3, pi over 2. This point is also 3, negative 3 pi over 2, isn't it? Couldn't I start here and go backward 3 pi over 2 as my angle? And then go up 3?
Counterclockwise.
I could go, well actually I would be going clockwise if I went that way.
Yeah.
But yeah. So, there's a new wrinkle. In rectangular coordinates, if I call this the point 0, 3, can I call it anything else? No. In rectangular coordinates, every point has exactly one name. In polar coordinates, points can have more than one name. This point is 3, pi over 2. It's also 3, minus 3 pi over 2. It's also 3, I could start here, go all the way around 2 pi, and then come pi over 2 again. So that would be, what's 2 pi plus pi over 2? 5 pi over 2. So I could also call that the point 3, 5 pi over 2. So how many different names are there for that point? How many is a lot?
Infinite.
An infinite. There are an infinite number of different ways that I can name that point in polar coordinates. And that's going to make some of our graphs interesting. The other thing we accept as an answer. I'm going to pick a new point here. Oh, somebody give me a new point. What's a good point?
5, 7 pi over 4.
5, 7 pi over 4. So 7 pi over 4 is here. So I got to come out 5. 1, 2, 3, 4, 5. There's 5, comma, 7 pi over 4. We would also accept this as an answer for this point. We would accept negative 5, comma, 3 pi over 4. So we do allow in polar coordinates for our radius, our r value, to be a negative number. So why, if this is negative 5, did I have to use 3 pi over 4?
Because relative to the 3 pi over 4, you're going negative 5 away.
Correct. If I start here and rotate to the 3 pi over 4, there's my 3 pi over 4 angle. By saying I want to go negative 5 means I don't go up its ray, I go down its ray. So we do allow for our r values to be negative. Questions on that? All right, my next question. We'll stick with this point, 5 comma 7 pi over 4. If I were to give rectangular coordinates, that would be x, that would be y. What's that point in rectangular coordinates? Something to do with cosine. Close. It's not just cosine 7 pi over 4 and sine 7 pi over 4, but you're very, very close.
We need 5.
We need something to do with the 5. That's right. All right, so look what I have here. I have myself a nice right triangle. If I want to know the value of x, and I know the hypotenuse is the length 5, and I know the angle, right? The angle is 7 pi over 4. So if I know this angle is 7 pi over 4, and I know that this distance is 5, how can I find x? Well, x, with this angle, x is the adjacent, 5 is the hypotenuse. So I would have cosine of theta is x over r. In other words, x is r cosine theta. So if I give you a point in polar form, you can give me the point in rectangular form. There's how you find the x. X is going to be r cosine theta. How about y? It's going to be sine, because if I'm dealing with y and 5, y would be the opposite over the hypotenuse. That's sine. So sine theta is y over r, and that's typically written as y equals r sine theta. So for the point 5 comma 7 pi over 4, so 5 comma 7 pi over 4 in polar is the same as something in rectangular, and x would be r cosine theta, which would be 5 times, what's the cosine of 7 pi over 4? What's the reference angle for 7 pi over 4? Pi over 4. What's the cosine of pi over 4? Root 2 over 2. And 7 pi over 4 is in quadrant number 4. In quadrant number 4, cosine is positive. So this is going to be 5 times square root of 2 over 2. So that's 5 square root of 2 over 2. And conversely, y would be 5 sine 7 pi over 4. That's going to be 5 times, what's the sine of 7 pi over 4? Negative root 2 over 2. Why negative? because sine is negative in quadrant 4. So that's going to be negative 5 square root of 2 over 2. So the polar point 5 comma 7 pi over 4 is the same as the rectangular point 5 square root of 2 over 2, negative 5 square root of 2 over 2. Questions on that? All right, give me a new, oh, this would be rectangular. Give me a new polar point. Anybody got a good polar point?
6, 5 pi over 6.
6, comma, 5 pi over 6. And that's in polar. And we're going to convert to rectangular. Okay, so x would be r cosine theta. That's 6 cosine of 5 pi over 6. That's 6 times something. What's the cosine of 5 pi over 6? What's the reference angle for 5 pi over 6? Pi over 6. What's the cosine of pi over 6? Square root of 3 over 2. So it's either positive square root of 3 over 2 or negative square root of 3 over 2. Negative. Why negative? Because 5 pi over 6 is in quadrant 2. That's a negative number. So times negative 5 pi over 6. So that's negative 5 pi. And y is our sine theta. That's 6 sine 5 pi over 6. Oh, wait. What did I just draw? You guys let me write that? What did we say it was? Negative square root of 3 over 2? So that's negative 3 square roots of 3. Don't let me write silly things. What's the sine of 5 pi over 6? 1/2, because we're in quadrant 2. It's a positive number. So 6 comma 5 pi over 6 in polar form is the same as negative 3 square root of 3 comma 3 in rectangular form. Questions on that? All right, now give me a rectangular point. Anybody got a rectangular point they like a lot? Nobody has a nice rectangular point?
4, 13.
4 comma 13. That's in rectangular. I want you to convert it to polar. All right, well, I think it helps to draw a picture. You can see where we're going here. You gave me the point 4 comma 13. That's right there. 4 comma 13. What I'm going to do is I'm going to draw myself a right triangle. So this distance is 4. This distance is 13. From that picture, how would you find r? Pythagorean theorem. You could use the Pythagorean theorem, right? R squared is 4 squared plus 13 squared. That's 16 plus 169. That's 185. So R is the square root of 185. And from that picture, how would you find theta? Inverse tangent, because we're looking for this angle right here. We would know from our picture that tangent of theta is opposite over adjacent, 13 over 4. So theta is the arc tangent of 13 over 4. I don't think that's a nice number, so I'm just going to leave it as arc tangent of 13 over 4. So basically we used two identities there. We used x squared plus y squared has to equal r squared. And tangent of theta is y over x. Questions on that?
Is polar mainly done in radians as opposed to degrees?
Polar is only done in radians. That's correct. Never degrees. We never use degrees in calculus anyway. How come we never, ever, ever use degrees in calculus?
Because they're not fractions.
Because they're not fractions? No, it's not that we have a love of fractions. How come we never, ever, ever use degrees in calculus? What's the derivative of sine x? Cosine x. And that only works if x is in radians. If you're dealing with degrees, the derivative of sine x is no longer cosine x. That theorem doesn't work. That's why we always, always, always use radians, never degrees.
Is there a theorem?
Oh, sure.
But we don't want to know, so don't ask it.
Yourself. Maybe you should take it.
Adam, I'm going to sit right next to you. Abel, take me.
If x is in degrees,
Well,
then what you have to do is convert it to radians. How do you take degrees and convert them to radians? Pi over 180. And then what's the derivative of sine of x times pi over 180?
pi over 180 cosine.
Oops. It would be that. So there's the formula you would have to use. Not as pretty, is it? Radians are better. All right, here's another point in rectangular form. How about the point -3, 5? That's rectangular. I want to go to polar. How do I find the radius?
Draw.
Pythagorean theorem. I'm going to find the radius by using the Pythagorean theorem. X squared plus y squared is r squared. So that's 9 plus 25 is r squared. So r is the square root of 34. And then how do I find theta?
Inverse tangent.
Tangent of theta is y over x. So tangent of theta is 5 over -3. So theta is the arc tangent of -5/3. Unfortunately, that's not the right answer. This point that I gave you, the point -3, 5, which quadrant does it live in? It's in quadrant 2. When I use this arc tangent function, what kind of angles does it give me? Angles in quadrants 1 and not 3, 4. If this is a positive number, arc tangent will always give me an answer in quadrant 1. If this is a negative number, arc tangent will always give me an answer in quadrant 4. That was our definition of arc tangent. In order to make tangent a one-to-one function and talk about an inverse, we had to limit our domain. So that's the wrong angle. It's in quadrant 4. It's supposed to be in quadrant 2. So how do I take that angle and put it in quadrant 2? Close, not pi halves. At pi. If I'm in quadrant 4, if I'm living down here in quadrant 4, and I really want to be over here in quadrant 2, How much do I have to add? Half of a rotation, right? So the correct answer is, the correct angle is pi plus arc tangent of minus 5/3. So that's something you'll need to watch out for. If your original point is in quadrant 2, or if it's in quadrant 3, you're always going to have to add pi to your angle to get it to be in the right quadrant. Questions about that?
It's the same answer if you subtract pi.
Absolutely. Another correct answer would be to subtract pi. A third correct answer would be to leave the angle as arc tangent of negative 5/3 and make that a negative square root of 34. So there are lots of different ways to fix it. I like to just remember, always add the pi. That's the way I fix it. But subtracting pi would work just as well. Other questions?
Is rectangular also known as Cartesian?
Rectangular is also known as Cartesian. Named after?
Descartes.
René Descartes. That's correct. Famous French. Mostly a philosopher. Did math for fun, kind of, but he was the first one to come up with the idea of the rectangular coordinate system, so it's named the Cartesian coordinate system after him. I don't know if there was somebody named Polar or not. I don't know.
Is there any other like coordinate systems other than polar and Cartesian?
Yes. There are cylindrical and there are spherical. See Calc 3. There are other coordinate systems. Spherical. Like a sphere. Yeah.
Also like 3D.
Yeah, so cylindrical and spherical are for 3D graphing. So cylindrical is based on cylinders, obviously. Spherical is very similar to polar. So you'll see those in Calc 3 when you do three-dimensional graphing. Other questions? All right, well, not only can we convert points back and forth, we can also convert equations. So there's an equation written in rectangular form. X squared plus y squared equals 9. What would that same equation be in polar form?
Circle.
It is a circle. It would be a circle in either form. That's correct. I want the equation in polar form. What's x squared plus y squared?
X is equal to r cosine theta, so it would be cosine squared r cosine theta squared.
R is the 9.
Yeah, awesome.
Would it just be r equals 3, so you get a nice circle around the plane?
What's x squared plus y squared? It's r squared. So this is the same as r squared equals 9, which is r equals 3. So notice how nice and easy the equation is in polar form for a circle. R equals 3.
That's it?
That's it.
Can't go back. Like if you were given like R equals 3, would you get
If I was given r equals 3, could I go backward? Sure, I would get x squared plus y squared equals 9. But what you would have to do, quite often, when you have just an r, what you need to do is square both sides. So you would square both sides of that equation, and you would write it as r squared equals 9. And then r squared, you would replace with the x squared plus y squared equals 9. So yeah, we can go either way. I can give you a rectangular equation, and we can convert it to polar form. Or I can give you a polar equation, and we can convert it to...
What if the circle wasn't centered at the origin?
What if the circle wasn't centered at the origin? Then it's harder.
Yeah.
All right, so you want to try one? How about, let's not make it too complicated. How about we did x minus 2 squared plus equals 9. So where's the center now? 2 comma 0. All right, how would you convert this one to polar form? Well, I think what I would do is I would FOIL this out. This would be x squared minus 4x plus 4 plus y squared equals 9. How does that help?
Your x squared and y squared just becomes r.
My x squared and my y squared, those become r squared minus 4. What can I do with that x?
The cosine theta.
X is r cosine theta equals 5.
What happened? Plus 4.
I subtracted 4 on both sides. That's where I got the 5.
Can you do with ellipses?
Yes. It's just harder. Unfortunately, we don't cover that section. If you're interested in learning more about that, if you go to section 10.6, it's called Polar Equations and Conics. So it shows you how to write ellipses, hyperbolas, all those things in polar form. We don't do it. But I'll tell you, they turn out to come out pretty easy. You get R equals ED over 1 plus or minus E cosine theta, where E stands for the eccentricity, and I forget what D is. D is the distance between the focus at the pole and its corresponding directrix. Whatever that is, you have to look at the picture. So it's interesting, depending on the sign of E and D, you get all of the polar graphs, or you get all of the conics from that picture, from that one equation. So this one equation will generate ellipses, hyperbolas, circles, and parabolas, depending on the appropriate values of E and D and the appropriate signs. So again, polar form is pretty good for things like that. All right, how about if I gave you a different equation in polar form? How about R equals sine theta. Any ideas how to convert that to rectangular form?
What would that even look like in polar form if there was numbers?
What would that look like in polar form? That's a wonderful question. You might notice on your calculator, you hit this mode button. We talked about parametric form. Your calculator can also do polar form. So I can go to y equals. I can type in sine theta. I can push graph. Oops, I think I need to change my window a little bit. I want to go from 0 to 2 pi maybe. Turn my axes back on. So what's that look like?
Ellipse.
It looks like an ellipse only because the graphing on the calculator is skewed. The distance of the tick marks in this direction is not the same as the distance of the tick marks in that direction. It's really a circle. So it's a circle. What you do, typically, notice that I don't have a formula for r, but I have a formula for r squared. And I also don't have a formula for sine, but I do have a formula for r sine. So what I want to do is I want to take this equation and I multiply both sides by r. take this equation, and that's a very common technique for converting polar equations into rectangular equations. Quite often you multiply by an r, or quite often you square both sides in order to get an r squared. So r squared is x squared plus y squared, and r sine theta is y. So you should recognize now that that is the equation of a circle. How do you know it's the equation of a circle? The powers are the same, the coefficients are the same, and they're both positive. That's a circle. Questions on that? How about this one? R equals sine of 2 theta. Look at that pretty picture. What do you call that? It's supposed to look kind of like a flower. So that's usually called a 4-petal rose. What if I change that to a 3 theta? You get a 3-petal rose. What if I change it to a 4 theta? How many petals are there? 8. So that's kind of interesting. When that angle is even, the number of petals double. But when that angle is odd, it's the same. So sine 5 theta has 5 petals, where sine 4 theta has 8 petals. Anyway, once again, with a graph like this, you start to get the idea of why would we want polar coordinates? How do you write that using x's and y's? You can't?
I don't know.
Oh, sure you can. Somebody already said it. Somebody said use the double angle formula. So I'm going to write sine 2 theta as 2 sine theta cosine theta. Now, unfortunately, do I have a formula for sine? No, but I have a formula for r sine. Do I have a formula for cosine? No, but I have a formula for r cosine. So the right-hand side, I want to write the right-hand side as 2 r sine theta, r cosine theta. So I can change my r sine theta into a y and my r cosine theta into an x. So what did I do on the right-hand side? I multiplied by r squared, so I have to multiply the left side by r squared. That gives me r cubed. Now I've got the next problem. Do I have a formula for r cubed?
You just split that up in r squared and r.
You're going to split it up as r squared and r? Okay. So r squared is x squared plus y squared. What's r? Well, r squared is x squared plus y squared. So r is not x plus y.
Square root of x squared plus y squared.
Square root of x squared plus y squared. But when you do square roots, how many square roots are there?
2.
2 of them. So we need r is plus or minus the square root of x squared plus y squared equals 2yx. Not a very nice looking equation in rectangular form. Much, much nicer looking in polar form.
But that won't look the same.
Sure it would. The difficulty would be, in order to graph this on your calculator, you got to get y all by itself. Good luck with that. You might be able to type this into Wolfram Alpha, maybe with just a plus, and convince it to give you a implicit plot, and my guess would be it would draw the top half, and then with the minus square root it would draw the bottom half. That would be my guess. Alright, in your book here they show you some interesting pictures. All right, so your equation, if you have r equals a plus or minus b cosine theta, or a plus or minus b sine theta, if a over b is less than 1, you get what's called a limicon with an inner loop. If a over b equals 1, you get something that's heart-shaped, so they call it a cardioid. And if a over b is between 1 and 2, you get a dimpled limicon. Pretty pictures. And then Rolle's curves we already looked at. And then they talk about circles and lemniscates. So you can use polar coordinates to draw yourself a nice infinity symbol if you want. All sorts of interesting pictures. So again, polar coordinates are kind of related to writing things in parametric form. The whole idea behind writing things in polar coordinates is you can get graphs of things, particularly things that are not functions, written very simply in polar form, not so easy to write in XY form. Questions about that?
What kind of things are these curves used for?
What kind of things are these curves used for? Well, again, a lot of them are used in computer programming and generating graphics. I mean, how do you think on a computer they get the infinity symbol as one of the symbols? They probably wrote it in polar form. Or all sorts of graphics and designs that you can do in polar form quite easily that you can't do in rectangular form. All right, the last thing we have in this section is derivatives. Let's say I give you r equals sine of 2 theta. Should have copied a problem out of the book. I need a point on that graph. Somebody give me a point on that graph. I'll pick one. 0, 0. Why is 0, 0 on that graph? Because if my angle is 0, 2 times 0 is 0, sine of 0 is 0. 0, 0 is an interesting point because 0, 0 is the same as if you're in rectangular coordinates or polar coordinates, isn't it? So is this a rectangular point or a polar point? It's both. That's correct. What I want to know is I want to know the slope of the tangent line at that point 0, 0. How do I find the slope of the tangent line? I have to find the derivative. But when I find the derivative, when you say derivative, you're talking dy dx, aren't you?
Could you do dr d theta?
I could do dr d theta. That would give me a derivative, but it would not give me the slope of the tangent line. The slope of the tangent line is always dy dx. So the question is, how do I find dy dx when I'm in polar form?
Convert to rectangle.
I could convert to rectangular. Do you want to take the derivative of that? No, me either. Here's the better way. And the better way is x equals r cosine theta, y equals r sine theta. Or you could write x equals r is sine 2 theta. And y is sine 2 theta sine theta. How does that help? what I really have now is I really have x in terms of theta. I have y in terms of theta. In other words, I have x and y written in parametric form. Except I'm using the letter theta instead of the letter t. When we did parametric, we always used the letter t. Now I'm using the letter theta. How did we find the derivative when our function was written in parametric form? We had dy dx was, we did dy dt over dx dt. The only difference is I don't have the letter x anymore, I have the letter theta. So to find the derivative, I need to write x and y in parametric form, and then I take the derivative. So I need to find d theta, dy d theta. How am I going to find dy d theta? I need to use product rule because I have multiplication right there. So I'm going to leave sine 2 theta alone. Multiply by the derivative of sine theta, that's cosine theta. Plus, then I leave the sine theta alone, and I multiply by the derivative of sine 2 theta, that's cosine 2 theta times 2. So there's dy d theta. Now I have to divide by dx d theta. Same thing, I use the product rule. I leave the sine 2 theta alone. I take the derivative of cosine. The derivative of cosine is negative sine. Plus, then I leave the cosine theta alone. I take the derivative of sine 2 theta. That's cosine 2 theta times 2. So my final answer is the slope of the tangent line. How do I now find the slope of the tangent line? Plug in a number. What number do I plug in? 0. 0 for theta. So I have to have this in polar form, theta. So I plug in theta. If I plug in theta, I get sine of 0. Sine of 0 is 0. I get sine of 0 there. It's still 0. 0 plus 0 is 0. Over, down on bottom, when I plug 0 into my sines, I get 0. But when I plug 0 into these two cosines, what's cosine of 0? 1, so this is 1 times 1 times 2. So the slope of the tangent line at r equals, or at the point 0, 0, just so happens to be 0. Questions on that? Okay, but that's how you're going to find the derivative of any polar equation. So if I gave you, give me another polar equation. R equals 15 tan theta. I wonder what that looks like. 15 tan theta. Interesting. Kind of like a hyperbola, except it looks like it touches itself. All right, so to find its derivative, I would write it as x equals r cosine theta, which is going to be 15 tangent theta cosine theta, which happens to simplify. That's 15 sine theta, because tangent is sine over cosine. Cosines reduce. And y is r sine theta, so that's going to be 15 tangent theta sine theta. That one doesn't reduce so nicely, so I think I'll just leave it like that. My derivative would therefore be dy dx equals, I take the derivative of y, so that's going to be 15 tangent theta cosine theta, plus, I leave the sine alone, sine theta, derivative of tangent, 15 secant squared theta, divided by, I take the derivative of x, 15 cosine theta. So there would be my answer. If I now wanted to find the slope of the tangent line, I would plug in whatever theta number they gave me, and that would be my answer. Questions on that?
So for these, it doesn't really matter that it's a function, like every x has more than one y. Is that because every point has multiple names?
Correct. These in general are not functions. In fact, this one we did is certainly not a function. But when we're finding dy dx, we're finding dy dx at one specific rectangular point. And it is possible that that one specific rectangular point could be written in multiple polar forms, but that's okay. We're finding the derivative at one point, so this formula that we use works correctly. Okay? Other questions?